So first I want to review a little bit what we've been working on, and we'll work into why we care about things like adjoint matrices. So the stories, we had this theorem about representation. Which is that V is an inner product space for all phi in V star. There exists a unique vector V such that phi can be represented as inner product with V. And from that, we introduced the concept of adjoint and a theorem or a definition theorem that defined the adjoint. That is, if I have two inner product spaces, and we're just considering them over R or C, and F is a linear map from V to W, then there exists a unique linear map we call F star, which goes in the opposite direction. And that map is called the adjoint, and it satisfies this adjoint equation, which says that an inner product in V and an inner product in W, we can communicate between them using these maps. So we have a V, we have a W, this is F star goes in the opposite direction. It's not the inverse, but it's the map that makes V F star of W equal to F of V inner product with W. And it's called the adjoint. We had a couple of different ways to see that it exists. It had some properties that we'll need to use a little bit today. And the properties were that it respects addition. The adjoint of the sum is the sum of the adjoints. That if I take the adjoint of a scalar multiple, this is in the field, I get the conjugate of the scalar multiple times the adjoint of F. And more generally, if I compose two linear maps, I can think of multiplying by A as multiplying by A times the identity. So this is an example of composing two linear maps. So if I compose two linear maps and take the adjoint, I can push the adjoint through the parentheses, but I have to switch the order of the maps. And if A, we think of this thing as being A times the identity composed with F star, with F star. Applying this is equal to F star times A times the identity, composition, star, and the star gets applied to the A to make it into an A bar. So that's what I mean by this is a special case. And the diagonal matrix A I V commutes with F. Sorry, it doesn't commute with F, but in this case it does, because F, because, what am I saying? Right, because F star has the right direction. Then we had some interactions with null spaces and ranges. Then the null of F star is the range of F perp, orthogonal complement, and the range of F star is the complement of the null of f. And you can get the other two by taking the adjoint of the expressions inside. Had that they interacted well with orthonormal bases in the sense that given a linear transformation, be a basis, a orthonormal basis of V, C, an orthonormal basis of W, then the matrix with respect to CB of F star, so F star goes from W to V, so we need the matrix to be CB instead of BC, is the conjugate transpose of the other matrix, the matrix BC of F. And then at this point, we're into the next chapter, and so we specialize to the case of linear operators. So forget about the VW for a moment, and we're going to just focus the rest of today on linear transformations from V to itself. V still an inner product space over RRC, and we'll zoom in a little bit on what the difference is between the real and complex case. In that context, we had the definition that a linear operator is self-adjoint or Hermitian I mostly say how self-adjoint if F and F star are equal. And if we have an orthonormal basis, the matrix of F star is the conjugate transpose of the matrix of F. So in a real vector space, we're talking about symmetric matrices. In a complex, we're talking about these conjugate transposes being equal. These had some nice properties, like every eigenvalue of a self-adjoint matrix is real. Self-adjoint operator is real. And some properties with respect to inner products, rotations. So, like with the rotation counterexample, I mean, if V is a complex inner product space, and F is an operator, and F of VV is 0 for all V, then F is 0. And that was false for real inner product spaces. And a couple of other theorems that were similar to that. But so the real thing I want to talk about today uses some of those results. And it's a weakening of the idea of being self-adjoint. Now, the reason is that self-adjoint operators that will turn out are extremely nice and have good eigenbases, have good invariant subspaces. But most of the things that the nice properties they have, at least in terms of diagonalization of matrices, don't really depend entirely on it being self-adjoint. Instead, a slightly weaker property is sufficient. So make the following trivial observation. If F is self-adjoint, then it's certainly true that F star equals F star F, because both those terms is just F squared. Of course, to make a generalization, you have to try to find out what property is important, there's no particular reason you think of that property, but it turns out that that's the property that's important. So that's the weakening of self-adjointness that we'll use. That is, we define an operator to be normal, and we'll get in a second another characterization that makes that word easier to remember, if f star equals f star f. And so every self-adjoint operator is normal, but not every normal operator is self-adjoint. For example, if I take, let's say, C2 with the standard basis and the dot product, the matrix, I can give you a matrix to define an operator, 2, 3, 2. This matrix is normal, but not self-adjoint. We can work out by computing these things. Couldn't be self-adjoint because it's real and it's not symmetric. Opposition. Here's a nicer thing to remember and something that's handy for proving some of the things we want to about normal matrices. So an operator is normal if and only if, so this we could have taken this to be the definition, it changes the norm of an input vector in the same way as its adjoint. And the proof that we'll use for this is the way that a lot of the proofs in this part will go, today will go, which is just as a series of equivalent statements. So f is normal is our first equivalent statement. Now that's true by definition if and only if f star equals f star f. Of course, another way to say the two things are equal, if they're vectors, and they are vectors in a vector space of linear operators, is to say that their difference is 0. And at least over the complex numbers, let's say this is complex, this is true if and only if that. Well, we can use the fact that over the complex numbers, the inner product being 0 for all v happens if and only if f is 0 over c, which implies that this is equivalent to, I can plug this thing now into an inner product, f star f minus f star applied to v, inner product with v equals 0 for all v. So that's an equivalent condition, at least over a complex vector space. And let's continue. So we have now an inner product with some addition going on inside, or subtraction. So we'd like to break that out by linearity. Well, that's true if and only if f star f of v minus f star of v equals 0. And I can, of course, change that minus to an equals. Get rid of the 0. So now we're starting to look something like a norm. Now we can use the fact that f is, or this is, we want to, go. We use the fact that f is normal, or this is true if and only if these two things are equal. Or you can think about it, if f is self-adjoint, we move it over. But it's a little bit weaker, the thing we need. We just need that f star f and f star are equal for all v in v. So fv squared equals f star v for all v in v. Okay, so the next couple of statements are about the eigenvalues and eigenvectors of self-adjoint and normal matrices, but operators. But first, let's talk about just arbitrary matrices. For arbitrary f linear operator and lambda in the field, I want to claim that lambda is an eigenvalue of f if and only if lambda bar is an eigenvalue of f adjoint. Again, we'll make some equivalent statements. And so it turns out in this it's slightly easier to say, not deal with the statement lambda is an eigenvalue, but to deal with the statement lambda is not an eigenvalue. So lambda is not an eigenvalue of f if and only if. We have lots of ways of characterizing that. One of them was to say that f minus lambda times the identity is invertible. To have an inverse means there exists a g, also an operator, such that, and remember this is invertible because we're in the world of operators. There exists a g such that g times this operator f minus lambda I v is equal, so it's the inverse on both sides, this 1g, g, and that's identity on v. And that's true if and only if there exists an adjoint g star such that f minus lambda I v star g star equals g star f minus lambda I v star equals I v. And that's true if and only if this f minus lambda I v star is invertible. Which holds if and only if f star minus lambda bar, if I take this was what I needed the addition, and so the adjoint of this plus that is the adjoint of this plus the adjoint of that, and then the adjoint of lambda times the identity is lambda bar times the identity, is invertible, which means that lambda bar is not an eigenvalue of f star. And that's true just for any f. Of course, for example, for a self-adjoint matrix, we know that for a self-adjoint operator, I don't know why I keep saying matrix today. For self-adjoint operator, the eigenvalues are real. So this is just going to say they have the same eigenvalues. And for normal operators, I don't need just self-adjoint, but for self-adjoint and also for normal operators in general, we can say more about the eigenvectors. So that one doesn't come with any guarantee that the eigenvectors are related, the last statement, but we can do that in the context of normal operators. So let's state this as a curly. Let f be a linear operator, which is normal. If v is an eigenvector associated to eigenvalue lambda, then an eigenvector of f, then v is an eigenvector of f's adjoint with eigenvalue lambda bar. So we get to use the same eigenvalues if we have a normal operator, eigenvectors if we have a normal operator. That's the content of that over this. So this tells me that the eigenvalues correspond up to conjugation, complex conjugation. This tells me that if it's also normal, the eigenvectors do as well. So suppose that lambda and v are an eigenvalue eigenvector pair, i.e. that f minus lambda times the identity applied to v is 0. Now if f is normal, if you work it out, see that f minus lambda I v is also normal. And by the other characterization of normal, f is normal if and only if, for all v, the norm of fv and the norm of f star v are equal. So, because f minus lambda I v has a non-zero vector v in its null space, this times v applied to v is 0 and has norm 0. It's a 0 vector. Because this thing here, f minus lambda I v, is normal, I could take its adjoint without changing the fact that without changing its norm. So this is f minus lambda I v adjoint applied to v. That's also 0. And I can put the adjoint inside the parentheses by going f adjoint minus lambda conjugate times the identity on v times v. Is another way to write that. But that exactly tells me that this thing f adjoint minus lambda bar I v, when applied to the non-zero vector v, must be 0 because it's something which has norm 0. So it must be the 0 vector. And so lambda bar is an eigenvalue. We already knew that. But more importantly, it's an eigenvalue with an eigenvector, non-zero eigenvector v. Remember, we had this statement that if F was a linear operator, I'll leave a blank space here, the eigenvectors of F corresponding to distinct eigenvalues are, and they were linearly independent for an arbitrary F. Linearly independent. Non-zero eigenvectors. If I add the hypothesis that this is normal, I get something stronger, which is that the eigenvectors are actually orthogonal. I get to drop the non-zero because 0 is orthogonal to everything. So there was, in this statement, there was a non-zero. I get to drop the non-zero because I don't need that anymore. So not only independent, they're more than independent, they're orthogonal. Proof. So to do the proof of this, we only have to compare two eigenvector eigenvalue pairs. So suppose I have two eigenvector eigenvalue pairs. F of u is alpha u. F of v is beta v. uv, let's say uv non-zero. Though they're trivially orthogonal if either of u or v is 0, so we don't have to worry about that case. Okay. So by the result we just obtained about the connection between eigenvectors of f and f star, we have that f star of v, we know what its eigenvalue is. It's just beta. If the other one, if the f of v was beta v, it's f star of v is beta conjugate v, and f star of u is alpha conjugate u. And now what we're claiming is that either alpha and beta are equal, so the eigenvalues are not distinct. If they're distinct, if this number is not 0, it must be that the inner product of u and v is 0. So we're saying that these two things, we want to show that the product of these two things is always 0. Either the eigenvalues are the same or the eigenvectors are orthogonal. So using conjugate linearity of the inner product, I can rewrite this as the difference alpha u inner product with v minus u beta conjugate v. Just move them inside. And that equals, because these are eigenvalues and eigenvectors, fu v minus u f star v. But I can take this f and move it over here, or alternately take this one and move it over here, taking the adjoint. So this difference here is equal to 0 always because of the adjunction. And so therefore either the eigenvalues are equal or the eigenvectors are. If these are not equal, then the eigenvectors must be orthogonal, because the whole thing has to be 0. So you can recall from the section on eigenvectors and eigenvalues that we care a lot about figuring out when a matrix can be made when an operator can be made diagonal. So if I have an operator and I have eigenvalues lambda 1 up to lambda m, then the following are equivalent. F is diagonal in some basis. F has a diagonalizing basis. V, this is saying the same thing, has a basis of eigenvectors of F, because then F will just be scalar multiplication in each of these invariant one-dimensional subspaces. Another way to say that sounds a bit different and requires some proof was that that V is equal to a direct sum of subspaces UI, each of which was F invariant. And finally, we had two further characterizations. I could write V as a direct sum of the null spaces associated, the eigenspaces associated to each eigenvalue. And then it was in fact enough to check that the dimensions worked out. We talked a little bit about how we could combine the notions of niceness that we've thought about. That is, a nice basis is one that diagonalizes the operator. A nice basis is one which is orthogonal, even better, orthonormal. And so the best thing we could ask for is an orthonormal basis which diagonalizes F. Not every F has such a thing. Of course, outside of an inner product space, it doesn't even make sense to ask the question, but we have an inner product space. We can demand that our basis be orthonormal. And we can ask that it satisfy all of these things. The answer to that question is the spectral theorem. So over the complex numbers, the operators that have a orthonormal diagonalizing basis are the normal operators, which is why we're so interested in them. And over R, they're just the self-adjoint operators. So let's state this theorem, the complex spectral theorem. We won't get to the real one probably until next time. Complex spectral theorem. Suppose V is a complex inner product space, and F is an L of V. Then V has, now I could have chosen any one of these characterizations, but let's say this way, V has an orthonormal basis consisting of eigenvectors of F if and only if F is normal. Which it would be in particular if it's self-adjoint. And so F would have a diagonal. The way of saying that is that F would have a diagonal basis in this orthonormal basis. Proof. One direction is easy thinking about the matrices that are involved. So suppose V has an orthonormal basis of eigenvectors of F. So the matrix, I only need one B because we're looking at linear operators on V. So both the domain and the codomain are equal to V, and they have basis B. The matrix is diagonal. We have an orthonormal basis, and so the matrix of its conjugate is the conjugate transpose of its matrix. So MB of F star is also diagonal, in particular. And so MB F star MBF equals MBF MBF star. And using the fact that the MB is an invertible linear transformation, it shows that F and F star also have this property, being normal. And that's because diagonal matrices commute. In the harder direction, we assume first that F is normal. Suppose F is normal. For any operator, in particular for F, on a complex vector space, not necessarily even an inner product space, we know already that there exists, on an inner product space, I should say, complex inner product space, there exists an orthonormal basis. E1 up to En. We didn't have that it made it diagonal, but we were able to show that there's one that made its matrix upper triangular by using the an arbitrary upper triangular matrix and then applying Gram-Schmidt, which preserves the nested subspace structure. Yes.
Did you say on the last?
Since diagonal matrices commute, that's how we know that's true. Diagonal if I multiply two diagonal matrices, the order doesn't matter. So that's why I can say that that equality holds. And then from that equality, you can deduce the equality of the operators. So there exists an orthonormal basis constructed by Gram-Schmidt from an arbitrary basis that makes it upper triangular, making MB of F upper triangular. So we have this matrix, A11, A12, A13, A22, so on, A and N. 0 below the diagonal, arbitrary entries above. And so, well, we have two options, right? We can either adjust this matrix somehow in order to zero out everything that's above the diagonal, or we can convince ourselves that it's already 0. So in this case, it's the latter that holds. They're already 0. However, we constructed this matrix as upper triangular basis, upper triangularizing basis of orthonormal vectors. All of the things above it have to be 0. So, and that you can do from a norm computation. So let's look at the columns of the matrix. So the first column of the matrix is the coefficients of F applied to the first basis element, E1. The norm of the first column of the matrix, or the vector represented by the first column, and the reason I can confuse those is because we have an orthonormal basis, I can compute that by squaring each entry. Right? It's the sum of the squares of the entry, but there's only one non-zero entry, namely A11. And so that's the norm. The squared norm is just the square of the absolute value of the first entry. Now when I think about the adjoint applied to E1, the matrix of the adjoint is the conjugate transpose. So the first column of the matrix of the adjoint is going to be just the first row of this matrix, but conjugated. Right? A11, E1, A12, E2, and so on, conjugated. When I take its norm, I can forget about the E1s. And I just get, it's the absolute value of A11's conjugate squared plus A22 conjugate squared, and so on. But since F is normal, F and F adjoint have the same effect on any input vector, so these two things are actually equal. And since these are all non-negative real numbers, it must be that all of these trailing terms are 0. Everything else is 0. And similarly, for FE2, FE3, and so on. We can show that the rest of those things are already 0. Need no further adjustment. I don't want to start the real spectral theorems. That's the end of the complex spectral theorem. The next thing is the real spectral theorem. I just want to say a word about why it's going to be different. So you won't be surprised to hear that it's because of these things, which are sometimes not solvable. Right? When I have a quadratic equation which has no real roots, that in some sense corresponds to these two-dimensional invariant subspaces. And that caused problems with upper triangularizability and things like that. And so in order to deal with the real case, we just have to adjust our argument for the complex case to deal with these special situations for the reals. But we'll put that off till next time.